Dear classmates, welcome back to the Testability Measure chapter. In the previous video, we have introduced the combinational scope. In this video, we are going to introduce the sequential scope. Similar to the case for combinational scope, the sequential scope can be divided into controllability and observability. SC0 of n and SC1 of n represents the minimum number of flip-flop assignments required to control a 0 or a 1 on node n. If you don't understand what flip-flop assignment means, you can also think of it as the number of clock cycles, which can be easier to understand. Similar to the case for combinational scope, a smaller number means it's easier to control the node. Sequential observability SO of n represents the minimum number of flip-flop assignments or number of clocks required to propagate the logic value on node n to a primary output. Please note that for sequential scope, we can only control primary inputs, we can only observe primary outputs, we cannot control flip-flop, we cannot observe any flip-flop. That means there is no scan DFT in the circuit. In summary, sequential scope testability measures the number of clock cycles needed to control or observe a signal. This table shows the way to propagate the sequential controllability SC0 and the sequential controllability SC1. This table looks very similar to the table of combinational controllability. For primary input, their sequential controllability are initially 0. This is different from the previous combinational controllability table. This is because we do not need to pause any clock to assign primary input, so their initial values are all zeros. For an AND gate, if we want to control the gate output Y to 0, because this is a controlling value, so we can either assign gate input X1 to 0 or gate input X2 to 0. So SC0 of Y is equal to the minimum of SC0 X1 and SC0 X2. Please note that we do not need to add a 1 at the end. This is because we do not need to pause any clock to control Y to 0. This is just a combinational logic. For SC1 of Y, we take the summation of SC1 of X1 and SC1 of X2. Again, there is no additional 1 here at the end. For the OR gate, inclusive OR gate, and the inverter, the numbers can be explained in the same way. For a fan-out branch, the SC of fan-out branches are the same as SC of fan-out stem. This table shows the sequential observability of node n. For a primary output, the SO value is 0 because we don't need to clock any flip-flop to observe a primary output. If we want to observe the gate input X1, we need to first observe the gate output Y, and we need to control the side input to 1. So we have SO of Y plus SC1 of X2. Again, we don't need to add additional 1 here because we don't need to pause any clock. We will skip the details for the other gates. For a fan-out branch, if we want to observe the fan-out stem x1, we need to only observe one of the fan-out branch. So we take the minimum of SO of y1 and SO of y2. This is similar to the case for combinational scope. In sequential circuit, we have flip-flop, which we don't have in combinational circuit. So we need to know how to propagate the controllability through flip-flop. Assume that this is a positive age-triggered asynchronous reset flip-flop. If we want to control the flip-flop output Q to 1, we can control the input D to 1, and we have 1 clock pulse. At the same time, we need to hold reset to 0. So CC1 of Q is equal to CC1 of D plus CC1 and CC0 of COK and the CC0 of R. Similarly, SC1 of Q is equal to SC1 of D plus SC1 and SC0 of COK and SC0 of R. But the difference is that we need to plus 1 at the end of SC1. This is because we need 1 clock pulse to control Q to 1. Now, if we want to control Q to 0, we have two solutions. We can either control reset to 1, or we can control D to 0 and pulse a clock and hold reset to 0. So we take the minimum of these two numbers. The difference between CC0 and SC0 again is that we have one additional 1 at the end of SC0. If we want to observe D of the flip-flop, first we need to observe the Q, and we control the clock, and we hold reset to 0. So CO of D is equal to CO of Q plus CC1 and CC0 of clock and the CC0 of R. Same thing here for SO of D, but we now have one additional 1 here. Here we show the sequential scope computation algorithm. Computation of SC and SO is very similar to that of CC and CO, but the only difference is that we require iterations for sequential controllability to converge. To compute the sequential controllability, for all the primate input, we set the combinational controllability to 1 and sequential controllability to 0. For all the other nodes, their CC and the SC are initially infinity. And when we propagate the controllability from primary input to primary output, from left to right in this direction, we iterate this until all the numbers stabilize. To compute the sequential observability, step 1, for all the primary output, we set their controllability to 0. For all the other nodes, we set their controllability to infinity. And then we propagate the probability from primary output to primary input. So from right to left in this direction. Please note that we do not need any iteration for observability computation. Now let me show you an example to compute the controllability. Please see this example circuit. This is actually our old friend, but now we add one flip-flop into this circuit. The input of flip-flop is J, and the output of this flip-flop is connected to C. Initially, we assign CC values to 1 and SC value to 0 to both primary inputs A and B, and also the clock. The other initial values are infinity. Now, starting from the primary input, we can compute the controllability level by level. First, let's look at this OR gate. The output of this OR gate can be computed by the equation shown in our previous table. The CC1 of the output of OR gate is equal to the minimum of the CC1 of gate input, which is 1, plus 1. So we have 2. But CC0 of the output of OR gate is still infinity because the flip-flop output Q is infinity. Similarly, SC1 of the output is 0 because the gate input SC1 is 0. Please note that we don't need to plus 1 for sequential controllability. Now let's move on to the second level. The value of J can be computed from the input of the inverter. So CC0 is now 3 because we need to plus 1 through this inverter. However, SC0 of J does not need to be incremented by 1 because this is a sequential scope. Similarly, we can compute the value of H, and then we move on to the next level. The CC1 of K is equal to 6, which is the summation of CC0 of input, which is 2 plus 3 plus 1, which represent the NOR gate itself. So we obtain this number 6. And the SC1 of the output K is 0. We can also compute the CC0 of flip-flop output Q, which is 5. This is because CC0 of J is 3, and the CC0 and the CC1 of clock are both 1. So 3 plus 1 equals to 5. But CC1 of flip-flop output is still infinity. For the SC0, we can compute the value using the CC0 of input D, which is 0, plus the CC values of clock, which are both 0. Don't forget to add 1 at the end because this is a flip-flop, so we need 1 here. Assume that this flip-flop does not have any reset, so we don't need to worry about reset in this example. In this way, we finish the controllability computation in the first iteration. Now it's time for you to practice. Given the numbers from the first iteration, please now continue to calculate the other CC values and SC values in the second iteration. Now please pause your video and do the practice. Are you done? The answers are shown in the next slide. Given the initial values from the first iteration, we can now do the second iteration. CC0 of the output of OR gate is now 7, which is 1 plus 5 plus 1, which represents the OR gate itself. And SC0 is now 1, which is gate input. Don't forget that we don't need to add 1 for sequential controllability. And the SC1 is still 0. Now we can move on to the next level and the next level. So we can now update the flip-flop output Q values. CC0 is equal to CC0 of D, which is 2, plus CC0 and CC1 of clock, which is 1 plus 1. So we have 4. And the CC1 of the flip-flop output is equal to CC1 of input, which is 7, plus CC value of clock. And the SC0 value is the same, and the SC1 of the flip-flop is equal to SC1 of the input plus 1, represent the flip-flop itself. So now we finish the second iteration. Starting from the values from the second iteration, we can now compute the third iteration. And we do it in the same way, and we finish the third iteration. We can see that all the values remain unchanged. So all the numbers are stabilized. So we finish the controllability computation. Now, let's try to generate a sequence of test patterns to control the flip-flop output C to 0. And the quiz number 2, try to generate a sequence of test patterns to control C to 1. Please assume there is no scan and we can only assign the value of primary input. Please pause the video and work on this quiz. Okay, are you finished? It is quite easy to control the value of C to 0. All we need to do is to assign B to 1 and then J is 0. So we pause 1 clock. After the clock pause, C would become 0. So this is quite straightforward. However, if we want to control C to 1, it is more difficult. We need to do two things. In the first cycle, we assign B to 1. And then in the second cycle, we would need to assign B to 0. In this way, we have 0 in the second cycle, and 1 in the second cycle. After we pause the second clock, C would become 1. So if we look at this value, we now understand the meaning of SC. SC0 equals to 1. That means we need only 1 clock to control C to 0. SC1 equals to 2. That means we need 2 clock pulses to control value of C to 1. So this is the meaning of sequential scope. Okay, with the numbers of controllability ready, we can now compute the observability. Initially, we assign the observability of the primary output to be zeros both for CO and SO. We can now move one level to the left. The combinational observability of H is equal to 3, which is the combinational observability of K plus the combinational controllability of the side input to be 0. So 0 plus 2 plus 1, which is the NOR gate itself. For sequential observability, the sequential observability of H is equal to SO of K, which is 0, plus the sequential controllability of 0 on the side input, which is also 0. Please note that we do not need to add additional 1 here, because this is a sequential observability. Similarly, we can calculate the CO and SO for J. Now we can move one level to the left. We calculate the CO/SO as is shown in the figure. For the output of the flip-flop Q, the combinational observability is equal to the CO of D, which is 3, plus the controllability of the clock. So 3 plus 1 plus 1, which is equal to 5. And the sequential observability of the flip-flop output Q is equal to the sequential observability of input D, which is 0, plus the sequential controllability of the clock, which are both 0. And finally, don't forget, we need to add 1 because this is a flip-flop. So we need to add 1 when we propagate the observability. So SO of Q is equal to 1. Now we move one level to the left. With these two fan-out branches, the observability of the fan-out stem is the minimum of the observability of 2 branches. Now we can calculate the observability of A and B to be 6, 0 and 9, 1. Now we have finished the sequential scope computation. It's time for you to work on this quiz. From the previous example, we know that the sequential observability of A is 0 and the sequential observability of B is 1. So quiz number 1, please generate a sequence of test patterns to observe A. Question number 2, generate a sequence of test patterns to observe input B. Please assume there is no scan, so we can only assign primary input. Please pause the video and work on this case. Now, are you finished? If we want to observe A, all we need to do is we can control B to 1. In this way, all the side input of AND gate and the NOR gate are non-controlling, so we can directly observe the value at primary output K. So actually we don't need any clock. So this is why the value of SO of A is equal to 0. For question number 2, if we want to observe the value b, it is not so easy. We cannot directly observe the value of b because the sign input of c is unknown. So we first need to assign b to 1 so that after 1 clock pulse, we control the value of c to 0. At this time, in the second cycle, we can assign a to 1, and in this way, the value of b can be sensitized to the output k. This is why the SO of b is equal to 1. This means that we need 1 clock to observe the value of b. So now you understand the meaning of sequential observability. In summary, in this video we have introduced the sequential scope testability measure. We introduced sequential controllability and the sequential observability. They represent the number of flip-flop assignments or clock cycles needed to control or observe signals. Smaller numbers means it's easier to control or observe the corresponding signal values. We assume there's no scan, so we can only control the primary input, we can only observe the primary output. And when we compute the sequential controllability, we would need iterations. Finally, we have an FFT for you to think about. So, in the previous slide, we mentioned that the sequential controllability computation needs iteration, and eventually the algorithm would be converged. But in what situation does the algorithm fail to converge? Can you give me an example? Thank you for watching.